So I suppose that you can hear me and you can see my screen, right? Can you guys see my screen?
Yes, sir.
Okay. So we are beginning this new chapter for Fourier transform. And to understand that, let me just remind you a few things from this previous chapter, Fourier series. So Fourier series and what we learned so far is the continuous time Fourier series. So what are the conditions before you can apply this Fourier series for signal? So the signal, let's say X is the signal, so it must be periodic. That is the first thing you need to remember. And the reason you are interested in this is that you will apply this signal to an LTI system, and LTI systems have this nice property, LTI systems, that if you apply an exponential, a complex exponential, and they preserve that shape and only get multiplied by a scalar, and that scalar, because this S is allowed to be complex, so that scalar is also allowed to be complex. That's all it can do, and that's why we say that this is an eigenfunction of this LTI system, and we also label this as H for that reason, and H of S is then the eigenvalue attached to that eigenfunction. This was the main idea, and this is why we wanted any signal X to be expressed as a linear combination. And yeah, we can write ck, and when I write k here, it means all possible integer values, and instead of S we chose j k omega naught t, and omega naught, because we need this X to be periodic, so omega naught was simply 2 pi divided by t. T was the period of that signal X, and you know how to compute these coefficients. I won't go into that again, but I just want you to think about something. So let's say you have done this computation, and now you have the k-axis, and you have this magnitude axis, ck magnitude, and maybe you have certain, so 1, 2, -1, -2, and let's say you have some value here, and then have some value here, and yeah, mm, some value here, some value here, and so on. It doesn't matter which shape you have. Maybe at 0 you also have some value. This is, and this plot we have a name for it. It was the magnitude spectrum, right? Magnitude spectrum. And similarly, we will have another plot where we will have the argument of C, right? So that maybe you have some values there and some values there, and so on. And if it's real, we also know that it happens to be an odd function, things like that. So this is our starting point for this new chapter. Now, this k was convenient because it's just a number, so it's very easy to think of C as a function of k, right? But we can also now look at it in another way. Instead of focusing on k, let's focus on this thing, which is k times omega naught. So k times omega naught can be thought of the kth frequency, the kth angular frequency, right? So what if I label it, and maybe if I choose some different colors, so this thing is important. That's how do I zoom this? Okay, so if I now mm, choose a different color, these are all okay. How do I choose color? Mm, So let's say I choose this, but yeah, I just choose black. Okay, I just want it to be different. So let's say here I have another, and instead of k, I want to have omega k, right? And that omega k is k times omega naught. So I'm just relabeling, yeah. So this one will become w omega 1, this 2 will become omega 2, yeah, omega minus 1, omega minus 2, and this will be omega 0, which is already 0. And now think about these spacings between any two omegas. And by any two, I mean any consecutive two, right? So what is the spacing between any two consecutive omegas? Can you guess? And let's call that delta omega. So I'm now using delta omega k for the spacing between the kth frequency and the k plus 1 frequency. So what will I get? K plus 1 times omega naught minus k times omega naught. Why? Because this is omega k plus 1 and this is omega k. So what do I get out of this? Hmm?
Omega naught just.
Yeah, omega naught. And we also know that omega naught is 2 pi by t. So now we have found a new meaning for omega naught. It is not only the fundamental frequency, fundamental angular frequency, right? It is also the spacing between consecutive frequencies. So it tells you how close these different frequencies are on the omega axis. And because it's connected to t, now I want you to think about the connection between the time period and this spacing. How are they connected with each other? What relationship do we have? Instead of, I mean, of course, you can say delta omega is, yeah, 2 pi by t, but it's they are inversely proportional, right? Can we say that they are inversely proportional? Yeah, because this is 1 over t. So if I have two functions and one function has a larger period, right? So let's break it down now. Let's say I will now have two functions, x1 and x2. So x1 is also periodic. Let's say you have this thing which repeats, yeah. So you have a periodic function which changes, yeah, like that, and this is the period, right? And let's say we have the exact same function, but this time it repeats after a very long time. So this is t1 and this is t2, right? Now imagine you have the Fourier coefficients for this one and the Fourier coefficients for this one, and you plot both. What difference will you see in those plots? For this one, yeah, these lines will have a smaller gap or a larger gap?
Smaller than.
Smaller gap, yeah. How can you say smaller gap? Because they're inversely proportional, right? So if t is small, this will be large, right? So this is smaller and this is larger. So this smaller means that delta omega k will be larger, right? And this larger means that delta omega k will be smaller. So now I'm asking you again, for x1, these spacings will be,
Larger.
yeah. So it means that now what if I push this to extreme? Can you give me an extreme case for this time period? How large can it be in the extreme case? Hmm? In the limit, we can say, what if I allow this t to infinity, right? So what kind of function do you get after that? Tell me. You have a function which may have some shape, but it never repeats, right? So it becomes a periodic. Got it? So you can go from, we can start with a periodic function or a periodic signal and allow the period t to change. So we increase it, we increase it, we increase it, and in the limit, we get an aperiodic function, right? So now we need to understand what happens to those Fourier, for what will happen to this plot. So how will this plot look like for an aperiodic function? Think about it. Hmm?
Like a continuous function.
It will be a continuous function because there will be no gaps. All the gaps will become zero. But how will it look like? Of course, we know it's continuous, but how? I mean, is it a continuous like that? Is it like that, like that? So now we need to look at another equation. This was, we only looked at frequency, right? So now we need to look at another thing. How was Ck calculated? If you recall the formula, it was 1 over t, right? And then you integrate over just one period. And what was this thing? Hmm, x of t exponential j k omega naught t and dt, right? And now this k omega naught, we can now replace this with k times, and that omega naught I know is also the spacings, yeah, delta omega k. So I can simply say k times delta omega k. What about 1 over t? We also saw that 1 over 2 pi by t was also omega naught, right? So that is also delta omega k. So if delta omega k is 2 pi by t, if I now divide both sides by 2 pi, what happens? This becomes 1 over t, right? And this becomes delta omega k by 2 pi. So I can now replace this thing, right, by delta omega k by 2 pi. You see something? Now think about that limit. What happened when we allow t to go to infinity? What happens to delta omega k? It approaches zero, right? So this approaches zero. This thing approaches a continuous variable, just like in your Riemann sum, yeah? So this will become a continuous variable omega rather than omega 1 and omega 2. And what do you get out of this? And what will happen to this integration? This is over one period, yeah? But now our period is infinite. So this will be minus infinity to plus infinity. This will become x of t. This will become, this was minus, right? Minus j omega t, no k, no omega k, dt. And what do we get here? What do we get here? D. This will become differential, right? D omega divided by 2 pi. This will be my new thing, right? So of course I cannot call it ck anymore. Whatever I call it, will not be a function of k, but a function of omega, right? It will be some function of omega. Let's use capital X for that. Apart from this 2 pi, right? I think, no, this is, um, I think this 2 pi has to go to the other side. Let's bring the 2 pi to the other side. And this 2 pi times, so I can even start here, yeah, I just multiply both sides by 2 pi so that I don't see this 2 pi there. So this 2 pi times ck will be my new function, yeah, in the limit t approaches infinity. Even now it doesn't make sense. This d omega is also there, yeah. So I should not use notation for Fourier transform, right? It will be something. I'll just call it something of omega, and maybe I can call it 2 pi times, instead of ck, let's call it c with some strange symbol, yeah. I just don't want to call it c. And now I want to bring this d omega here, right? And now you have, now this looks very similar to, well, actually it's exactly the Fourier transform you saw in that CVT course. So this is what you already know, and it naturally arises when you push t to infinity. So whenever you turn a periodic function into a aperiodic function, what happens to these Fourier coefficients? They get smaller and smaller, right? Because this goes to 0. So if I go back to that plot, this plot will not only become continuous, but it will literally become 0. It will just see zeros because this ck will have that d omega in it, and it will be 0, literally 0. So there is no point in looking at this, right? That is why what we did here, that this d omega has to be moved to the other side. Only then you can have a quantity which you can plot. But here we change the meaning. This c was the Fourier coefficients. So if c was the Fourier coefficient, and remember what was the meaning of the Fourier coefficient? It told you the contribution, right? What was the contribution of the kth frequency, right? So of course you cannot say kth frequency anymore. You will say what is the contribution of omega, because you don't say omega 1, omega 2 anymore. So, and then you divide by d omega, and yeah, I mean, whether you multiply by 2, actually you can multiply by 2, that's better. So now you can say that it is not the Fourier coefficients as it is, but divided by d omega. And d omega is actually a change in frequency or frequency interval. So it's kind of density, right? So if the ck's were spectral coefficients, we call them spectral. These ck's in the Fourier series, for us they were spectral coefficients because they told us how much of a particular sinusoid we need in terms of amplitude. But here, because of this d omega in the denominator, we cannot call them coefficients or spectral amplitudes anymore because they all become 0. If I bring this d omega back to the other side, it becomes 0. So dividing, actually, it's very neat. Yeah, you divide a very small quantity by another small quantity, and you get a density. So this is your spectral density. So we discovered Fourier transform as the density of Fourier coefficients x. And you can get rid of this 2 pi as well, right? If I start with something, let's see, with a head, with a tilde, and instead of d omega with the 2 pi, I bring this 2 pi in the denominator. And because pi is 2, omega is 2 pi f, the cyclic frequency, omega by 2 pi will be f, and d omega by 2 pi will be df. So you can even think of it as spectral coefficients divided by df cyclic frequency. So it's really density, yeah, coefficients per unit interval of the cyclic frequency. So that was the big picture, and I don't think you can turn this discussion into computations. This was only a motivation for why we need Fourier transform. So we were comfortable with the idea of Fourier series, but that was limited to periodic functions. We wanted to use the same idea for aperiodic functions. So rather than attacking aperiodic functions directly, we started with the Fourier series by pretending that it is periodic, but we know it's not periodic, so we say, okay, the period is made larger and larger, arbitrarily large, and that turned out, so these coefficients turned out to not only fuse into each other to become coefficient, but they also got smaller and smaller, literally becoming zero. And to avoid that zero, they became zero because of this 1 over t, 1 over t, and that 1 over t was actually related to d omega, and we divided everything by d omega, so we got a nice function, and this function will not be zero. So that's why the Fourier transform doesn't become zero everywhere, because you got the problem to the other side, but the meaning changed. Now you call it density, right? If you have followed this discussion so far, right, um, it should resonate what you learned in probability. In probability, you started with PMF, right? I'm just summarizing that as well. And then I get to computations. You started with PMF, but PMF requires a discrete random variable. And when you want to deal with a continuous random variable, and if you try the PMF idea for that, you get zero, everything becomes zero, right? Because there are infinite number of points, so you cannot assign non-zero probability to every point. So you have to assign zero. But what you do the same trick there. So stop looking for PMF, but divide the PMF by some interval, and you get a density, and that is your PDF. Yeah. So PDF is to PMF in the same way Fourier transform is to Fourier coefficients. They are both densities, and they solve the problem of going from discrete to continuous. So I hope you got that, and we now get to the slides. The slides will now make this more explicit. So he also now reminds you that Fourier series is an extremely useful function representation, but unfortunately this representation can only be used for periodic functions, since Fourier series itself is periodic. Many functions are not periodic, we know that. So rather than abandoning the Fourier series, you can start with the Fourier series, and then you apply that limit, which I already did, and you get the coefficients actually are replaced now by what you now will call Fourier transform. Yeah. And this is a, I mean, he wrote all of those things in just one equation. This is our original function. We want to express this as a Fourier series, so this whole thing is simply ck, but then he looks into it, he writes the formula, and you observe that 1 over t, and when you apply this limit, that 1 over t, yeah, appears in the form of d omega by 2 pi, right? And that ck, right, becomes something of omega times d omega. So x of omega times d of d omega divided by these three things together becomes the approaching object of ck, and you get this Fourier transform for free, right? But the meaning changes. Yeah, here the meaning of ck was how much weight do you give to each sinusoid. Yeah, because this is a complex sinusoid, so it's an amplitude. Yeah, ck was appearing as a complex amplitude of the sinusoid. Here x of omega is not the amplitude, it is the density. Why? Because it must be multiplied by d omega. Anything that must be multiplied by d omega to get the contribution cannot be the amplitude, it must be density. So you can think of this as the density of C. And we are done with that, okay? So, but all this is only possible if this integral, right, which we want to call x of omega, the transform, this must converge. So what if it doesn't converge, right? So you might think that, oh, it will converge for most functions, but you can easily see that if you think about this integral, it is from minus infinity to plus infinity. That's the first thing you need to note. The second thing is that the convergence has to come from x. This cannot help you. Why can this not help you in the convergence of this integral? Any idea? Hmm? Because when you multiply something, that will only help if the magnitude of that thing drops, and this magnitude is always 1, right? So the exponential minus j omega t, the magnitude is always 1, right? So when the magnitude is 1, this will not help you in any way. So x has to be such that it converges. So so if the integral doesn't converge, then this function cannot help you. And that is why if you try this integral for constant functions or for periodic functions, although this idea was developed for aperiodic functions, but what if you said, okay, I want to apply it to periodic functions, and or I want to apply it to unit step, or I want to apply it to signum function. In all these cases, if you try this integral, it will not converge, right? So it means that this formulation, like whenever you write this integration of something, and whether you write this or not, right? This is typically viewed as a Riemann integral, right? Because he discovered this. And Riemann integration requires this integrability. It must be absolutely integrable. You know it from calculus. But what do we do with these functions? We don't want to abandon these functions, right? We still want to be able to work with these functions. So, how do we solve this problem? The solution is similar to what we did with delta, right? We Delta was a generalized function, right? So normal function concept doesn't work. So we say, okay, let's generalize the concept of function. So here we can do something similar. Instead of just working with the classical Fourier transform, which is an integral of this Riemann form, we just say generalized Fourier transform. So generalized will allow the use of Dirac delta to solve these problems, right? So now you will see this generalized Fourier transform requires advanced calculus, but we're not going into that. We'll just use some shortcuts related to the generalized function, and yeah, we will use those results without proofs. So, but I'll try to convince you without proving anything. So this is how your typical this when I say classical or traditional, I mean not generalized, yeah, set of mere Fourier transform. So the formula is, already. You start with the function, you multiply it with this complex exponential with a negative sign there, and you integrate over all the real values, and you get your Fourier transform. Yeah, and this is one way of writing it down. Just write a capital X, and another way is to just apply this Fourier transform operator to X, and then evaluate it omega. That's another way. And if you want to, and this will be our forward Fourier transform equation. You can also call it the analysis equation. Just like we had the analysis equation in Fourier series, we have the analysis equation in Fourier transform. If you go in reverse, for the inverse transform, you start with the Fourier transform. This time you multiply with another exponential, which is the complex conjugate. Now this time integrate with omega rather than t. and you have to use that 1 over 2 pi because that had to be cancelled, and you now you have the inverse transform. So this will be our synthesis equation. So analysis, synthesis, forward, inverse. This is the same language we were using in Fourier series. So let me just show you one example and then I get to this generalized thing. So I'll just show you quickly one example of how, although you have done these computations and in CVT, but I just want you to see. I'm skipping all these pages because this is related to the proof, which we already did. So I'll get to this later because this is related to the generalized. Okay, so this is the thing which you can now understand easily. This is the Fourier transform of the rectangular function. And here you don't need generalized. You can just go with traditional Fourier transform. So let's say we have a rect function, which will look like that. And you apply this integral to the rect function. And you know the rect function is only from minus half to plus half, right? So the limits are practically minus half to plus half. And the value is 1. So you just have 1 there. And then all you need to do is to apply this integration, right? So I want you to follow this evaluation carefully. This far you can go very easily. You just apply the limits and change the limits to minus half to half. Can you spot any problem in this way? He has done just like you would do in calculus, right? You apply the formula, antiderivative, then apply limits, get this far. There was something similar in Fourier series when I told you not to do it like that. So what is the problem here? I want you to see the problem. I won't allow you to do it like this, right? So can you recall that technical issue with the Fourier series? There we had CK and we had similar problems. So let's actually carefully look at the steps, right? So this is okay? No, this is not okay. Why? Because this has divide by omega, and this requires omega to be, tell me.
0.
So you required omega to be 0 so that you can divide by 0, right? It must be non-zero. So if you want to do something like this, you have to declare, right? For omega non-zero. And then you won't have this thing. You will just go this far, right? And then what you need to do, for omega is equal to 0, you have to have a separate case. So for omega is equal to 0, you have to have a separate case, and you have go back to this. So what happens here? What happens when you set omega to 0? This becomes 0. So what do you get out of this? Minus half, half, and exponential 0 is 1. So you just have dt. So what do you get at the end? Hmm?
1.
So you will have to write it like that. That x of omega, I'm now writing it, okay? You need to take note of this because most of the examples in this book, they won't pay attention to this. Um, but I will not allow you to do that, okay? You will have to remember this, both in Fourier series and in Fourier transform, because the problem is the same. So when omega is non-zero, you have this thing, right? Which is, I'm just copying it. Sine of omega by 2 divided by omega, right? And I can even bring that 2 here. So omega by 2. And when omega is 0, what did we get from there? 1, right? And now this thing can be written as sinc of omega 2, omega by 2. Why? Because this is how we define the sinc function. When omega is non-zero, we use this formula. When omega is 0, we use this by definition. So here you can say x of omega becomes sinc of omega by 2, right? So you can see that in this integration, we didn't need any, we did not have any problem with convergence. Yeah, the integral converged very easily. But if you try something like that, let's try the same thing for unit step to see the problem, right? So let's pretend that this is u of t, right? So instead of rect t, you have u of t. So how will this change now? Hmm? This will become u of t. This will become minus infinity to plus infinity. And now we can actually write it there. So it will be, because u is 0 from minus infinity to 0, so the limit will actually be from 0 to infinity. And u of t is 1 there. Now try to think about this integral. Will this converge? Hmm? This won't converge because this is a constant signal, yeah? The value of a constant signal, and this thing is not helping. So there is no way, it's not absolutely integrable, and you can't solve this problem. So that's why you need the generalized Fourier transform, the tricks. So rather than attacking this directly, we will now attack this problem indirectly. So let's solve another problem. Let's solve, yeah, the impulse, for the impulse. So what will be the Fourier transform for the impulse? Let's try it on a different page, yeah? Let's apply, let's try the Fourier transform of the impulse. And it will be a good exercise because I will also tell you how you will have to write it properly. So I start with delta, you say f of delta, and maybe you can have this bracket in your mind. And I want to, what should I write in the bracket? Tell me. Hmm? If this was x, what will I do? I will say I have the signal x, I want the Fourier transform. Once I have the Fourier transform, then I want to evaluate it. At what? You can't write t there.
Omega
Yeah. No,
t.
you can't write t. You can't write t there because you have the Fourier transform. This is transform will be evaluated at omega, right? So never do this. If you say this will be wrong, right? If you write it in this way, this will be acceptable only in one case. Can you guess when? Because if you apply the similar interpretation, if you say x is a function and t is a number, this has to be done first, and then you can't do this, right? I mean, mathematically you can do it, but it will not be meaningful. So what you do, you think of t as an indeterminate, right? Which I typically call coordinate, right? And then x of t is an expression which stands for a function, yeah, because t is not a value, t is not a number anymore. So x of t now stands for the function, and you can now apply transform to it. So that is the only case in which you can work. That's why symbolic toolbox allows this. So let's work with this now. We want to evaluate this at omega. So how do we do? We start from minus infinity to plus infinity, right? The function is delta, so we write delta of t, and then exponential minus j omega t, and then dt. Which property do we need to solve this integral? Which property of delta do we need to solve this integral? Can you recall the name?
Shifting.
Shifting property. So because of this delta, this function will only matter at where the delta is located, and delta is located at 0, right? So you have to set, which thing must be set to 0? T or omega? Hmm?
Omega.
Why omega? Delta is a function of t. So how can you say this omega is only for the final evaluation, right? So you have to do it like this. It is simply minus. So the only thing which matters is 0 minus 0 plus, right? And delta of t. And in that region, this will be simply exponential minus j omega times 0. Omega doesn't go anywhere, right? So what do we get here? This is 1 and this is also 1. So the Fourier transform of Dirac delta is simply a constant function, right?
Sir, can you explain this again?
Which part?
Say the impulse one. How did we get one?
Yeah, but you said it's shifting property, right? In shifting property, this delta is 0 everywhere except at 0. So this function gets multiplied by 0 throughout this integration interval. The only place where that multiplication by 0 is not done is at 0, right? So that's why we change the limits to 0 minus 0 plus. Yeah.
Okay.
So this is our
Thank you.
real line from minus infinity to 0 minus, then 0 plus to infinity. So here everything gets vanished. Here everything gets vanished. This is the only thing which matters. So that's why I change the limits to 0 minus 0 plus. And in that limit, this function has a value of 1. Why? Because t is 0 there. Yeah, t is 0. So okay, let's try something else now. Uh, so I started with the impulse function, right? And I tried to compute the Fourier transform. I want you to look at this formula, right? This is the inverse transform, right? And let's try to use this formula to find the inverse transform of delta. So what are we trying to achieve? What we learned so far is that if we have delta, the continuous time Fourier transform will be a constant signal 1, right? And this 1 is viewed as a function, not as a number. And even if you write this t, and if this t is indeterminate, this still works. Now we try something different. We want to see what should be here if instead of 1 here, if we have delta. So what should I write here? Delta of? Hmm? This is CTFT. So this will be a function of time, some function of time, and this will be
Omega.
omega. So we are asking for the inverse question. What is the function, what is this time domain signal for which the Fourier transform, the continuous Fourier transform is delta of omega, right? So how do we do that? We use this integral, yeah, this one. Pay attention to this, 1 over 2 pi minus infinity to plus infinity x of omega exponential j. So let's do it here because I want you to think about this. If you just copy it from there, it won't work. So I want basically the inverse transform of delta, and this will be evaluated at, tell me, hmm?
T
Now we will have to write t because
delta
this is,
T.
sorry, this is the transform. We took the inverse. Now we have the time domain signal. Time domain signal will be evaluated at t. So what is the formula? 1 over 2 pi, right? Minus infinity to plus infinity, and we have x of omega, right? Here we must have x of omega. So we have delta of omega, right? Not delta of t, right? This t is the thing on which we evaluate the inverse transform. Delta is not the inverse transform. Delta is the function for which we find the inverse transform. Here we'll have exponential j omega t, and here it will be d. Tell me,
D omega.
d omega. Yeah, because we started with the transform. We are integrating the transform, and this is the complex conjugate, right? Now let's try to evaluate this integral by the same method which we just did a while ago. Hmm? What will you get? 1 over 2 pi. Same method, yeah. It only matters at 0. But this time, what will be replaced with 0? Omega, right?
Omega, sir.
Now this time t will be spared, right? So it's simply 0 minus 0 plus, and this will become 1, and this is actually 1. So it's just 1 over 2 pi. Another constant signal, another constant function of omega, right? Now let's try something else. What we learned is that the inverse transform, now we can go back to that, yeah? This is what we were looking for. So what should I write here now? The delta of omega is the transform of 1 over 2 pi. Now, if you carefully look at these integrals, whether it's the forward transform or whether it's the backward transform, inverse transform, all the operations are linear, yeah? You just have integration, yeah? And you multiply by a time dependent function, but multiplying by time dependent function is still linear. Of course, it is not it is not time invariant, but it is still linear. So it means that if I had started with, if instead of delta, if I had started with 2 pi delta, right? And I repeat this, what should I get here? Instead of delta, I want the inverse transform of 2 pi delta. What will I get at the end without repeating all that thing? I know everything is linear. So it will be, tell me,
One.
it will be 1 because it's just linear, yeah? So you multiply both sides by 2 pi. You can multiply both sides by 2 pi because it's a linear operation. All the operations are linear. So we discovered a new transform pair. Instead of starting with 2 pi, with 1 over 2 pi, sorry, instead of starting with delta only, if we start with 2 pi times delta. So now look at these two pairs now. Constant 1 is the Fourier transform of delta, and 2 pi delta is the Fourier transform of 1. Yeah, it's a kind of duality, right? Can you see something here? This is I want you to appreciate something. What if so we discovered this. Let me remove this. We computed this directly. Yeah, we didn't do any trick. This was direct computation. But this was indirect. Why? Because we didn't start with 1. What if we start with 1 and we try direct computation? So let's say I want the Fourier transform of 1, right? Which is, I want to see this one as a signal, and I want this. What will I do? I will start with minus infinity, plus infinity, right? 1 is x of t exponential minus j omega t dt. What was the problem which we just came across a while ago in the slides? Do you see that discussion? I don't know where was it, but I told you that it was not, yeah, convergent, yeah. It is not converging. I don't know where I wrote this down. But this integral will not converge. Why? Because the limits are minus infinity to plus infinity. This one will never drop to 0. It won't even change. And this, when you try the absolute integrability, the absolute value of this is 1. So this will not converge. So you will say it's infinity, right? You will say it's infinity, but infinity is not is not a meaningless object. So we simply say it does not converge. So can you now explain to me, in direct computation it doesn't converge, but in indirectly we got to know that 2 pi delta is the transform of 1. Actually, we did this here. So why does this work and why does this not work? How will you explain this? Hmm? This doesn't work because we are using the classical Fourier transform. This integral is the Riemann integral, and Riemann integral doesn't work here. What we did here, because it was indirect, we didn't see what kind of integration will be behind the scene, and we don't want to get to that theory. So this is actually not the usual transform. This is the generalized transform. So the reason you saw this magic is because you don't see things going behind the scene. And we avoided that scene by using the inverse transform. So inverse transform actually avoided the bottleneck. Do you get this point? And one indication of that that convergence issue is that delta itself, yeah, is not a usual function. It's a generalized function. So the fact that you see delta on the right side is a proof that it is not the classical or traditional transform, it is the generalized transform. I hope you get that point, right? So whenever we,
Um,
yes,
so how are we seeing this one in frequency domain? How does it look like?
oh, okay. So you want to see the spectrum, right?
Yes.
Yeah. So before that, if I just go, actually, you should have asked this question here when we started the rectangle. So we started with this rectangle, we worked out these transforms, and unfortunately, he has not plotted it, but you can actually plot this thing, this sink of omega. You can plot the sink of omega. How will a sink of omega look like? So if you have this transform, this rectangle function in time domain, and you transform it to CTFT, that sink will look like this, right? And if you want to turn this into magnitude and phase, so magnitude plot, because it has to be positive, so it will look like this. You take the absolute value, and similarly you will have some phase plot, right? So we want the same for 1. So now I have in time domain, I have this delta, right? And I take the Fourier transform, right? And in here, I have constant 1. So now, this is omega, and this is constant 1. Let me use a different color now. Constant 1. This is the Fourier transform of delta of omega. So it means constant magnitude, right? And what is the meaning of Fourier transform? I told you in the beginning of this lecture. If this was a Fourier series, what would be the what would have been the meaning of this thing? It would have been the amplitude, right, of that frequency. So at each frequency, you would be having amplitudes. We can't use the word amplitude here, so we have to call this what? Spectral density. So you can actually see this, okay? So what this actually tells you that delta of t can be constructed not as a sum, because that would be only possible if it were periodic. You replace that sum in the Fourier series by an integral. You have this 1 over 2 pi, and here you see the x of omega. So instead of x of omega, you have this 1, right? And you have this j omega t d omega. Try to read this equation. In order to get this function in time domain, you need all the frequencies. One means that I need all the frequencies. Yeah. And all the frequencies must have the same density, because this is density, yeah? The same density to construct it. Can you now explain why this is the mathematical fact now? How can you convince yourself why would someone need all the frequency to get this signal? Think about it. And I want you to hold this for a while. Let's ask another question. We also discovered another thing, right? In time domain, let me change the color again. In time domain, we started with the constant function, right? The constant function 1. And we saw that the Ct of t was a delta, right? 2 pi delta. Think about it. Sorry, no, it's not t, it's omega, right? How many frequencies do you need here? Can you tell me now? To construct this constant signal, how many frequencies do you need? This is density, right?
Single frequency.
A single frequency. That is why it's called DC. Zero frequency is just one frequency. You need single frequency, but the density must be infinite, right? Infinite density. If it was not infinite density, let's say this was a finite density, yeah, that wouldn't work, because the integral, uh, the area under this would be, have been 0, and you got 0. You don't get 0. DC is you need a constant value. And here, although you have just one point in time, but this function is so weird, this changes so rapidly. Like if you think about it in informal way, like I call it desi way, huh? So you start from 0, and you before 0 you go to infinity and then come back to 0. I mean, of course, this is a crude way of talking about it, but you can see how fast things are happening. Things are so fast that to construct them as an integral, you will need all the frequencies. So it's an infinite frequencies. So from this, you can learn that if you look at the spectrum of the Fourier transform, the wider the spectrum, right? This is an extreme actually. So if a spectrum is wider, then let's say there is one signal x, and you take the transform, and the spectrum here is wider, and another signal y, and the spectrum here is narrower. It means that this must be a faster signal because you need more frequencies to construct it. This will be a slow signal because you need just a few frequencies, um, or frequencies in a narrow range to construct it, right? Let's see if we can have any other things. You can look at these slides yourself. I have discussed these things in other lectures. Yeah, the dot notation, and when can you replace the dot with a t, arbitrary, indeterminate. I don't want to discuss this. Yeah, I have been telling this many times. Convergence. He is discussing the issue of convergence, which I already did. Yeah. So point-wise convergence is only possible if you have absolutely integrable functions. When the functions are not integrable, so the trick we did, uh, because the trick we did use is delta, that works everywhere, but normally for the classical transform or for the Riemann sum, you you look for this finite energy thing, right? The energy must be finite if you want a classical traditional Fourier transform. So the energy, um, so the convergence will be in mean squared error sense, but that is something we already know from. Okay, I also want you to press P in this chat window, right, for the attendance, each one of you. So you have similar issues, yeah. We did what we saw in Fourier series. You have these Dirichlet conditions, yeah, and we already saw this. None of these satisfy that condition. So if a function satisfies the Dirichlet conditions, if it is absolutely integrable, then everything is fine. It's pointwise converging. So if it is Dirichlet, if it satisfies Dirichlet conditions, you have to remember these things, yeah. The average value, yeah, the constructed signal will convert to the average value. So all of this is just a repetition of what we saw in the next lecture. We will discuss properties of Fourier transform, right? These properties, and you have to learn these properties properly in order to apply, because we'll be more in this integration. I did only to discuss certain things. I won't expect solving these transforms or inverse transforms simply by integrations. I would like you to use these tables to get that, right? So I can now stop the recording.